Today our talk is gonna go through deep learning for biomedical signal processing applications. Will be delivered by our esteemed guest, Professor Awad Al-Zaben. Um, uh, Regarding uh, So IEEE is we are the Jordan section of the Institute of Electrical and Electronics Engineers. For the This institute has been formed 1884 and it has been running till now with a huge number of participants all over the world, with many of the very big names in electrical engineering and computer engineering have been contributing to this institute. Uh, so we are in Jordan. We are the IEEE has divided geographically its region into 10 regions, and in Jordan we are part of Region 8, which consists of Middle East, Africa, and Europe. So it's a large region, and the IEEE Jordan section is one of the very active sections within Region 8 and within global IEEE. This year, we have got a new record into our member numbers, and we have now more than 3,500 members that are registered in IEEE. A very big number that shows how much people are perceiving IEEE and its activities within Jordan. We have around six society chapters that are actively working in Jordan. The Joint Power and Energy section. We have also the Joint Signal Processing and Communications. We have also the Industrial Applications section chapter. We have also the chapter of Joint Computational Intelligence and Computer. We have the Robotics and Automation Society, and we have also the Engineering and Medicine in Medicine and Biology chapter, which I represent in this talk, and which has been part of organizing this talk. We also have affinity groups. We have Women in Engineering group. We have the affinity group. We have Life Members affinity group. We have the IEEE Young Professionals also affinity groups. So these are three affinity groups that are also active in Jordan. We have more than 22 student branches distributed all over our country in private and public universities. And as you can see, these student branches have been also active on opening new society student chapters. So all the professional student chapters, they have also another counterpart, which are student chapters. We have also initiated a new local group, which has been established by Dr. Musa Al-Akhras and me. And in this local group, we are focusing on activities related to machine learning, deep learning, computer vision, and large language models. And part of this local group, we are organizing a monthly talk, of which you are all here for this second talk. The first talk was the last month by a professor from Saudi Arabia, and this time we are hosting Professor Awad Zaben from Jordan. I don't want to take a lot of time. We are all waiting for a very nice evening lecture with Professor Awad. Professor Awad will be our host for this evening. He's a distinguished faculty member in the Biomedical and Medical Informatics Department at Yarmouk University. He has a master's and PhD from Colorado State University. He has a very extensive research experience in biomedical signal processing, pattern recognition, classification, medical electronics and instrumentation, and biomedical modeling. He has contributed significantly. He has contributed significantly to the field with numerous journal publications, and he have 2 registered patents. So he's a senior member of the IEEE and a co-founder of the EMBS Jordan chapter. His achievements, he has a large number of achievements that can express his activeness in this field. But some of his well-known achievements is the best patent award that he got in 2016 from Philadelphia University, and then also the Hisham Hijawi Academic Distinction Award for teaching and scientific research in 2005. Please, so the topic will be concerning deep learning application in biomedical signals. I'm sure we are all looking forward for this lecture, and I hope it will be a very nice evening for everyone. Welcome, Professor Awad. I will give you the host to this meeting so that you can now control the talk moving forward. I hope we can have at the end 10 minutes of question and answers for whomever who would like to have some questions based on the lecture.
Thank you, Dr. Hisham. Am I host now?
Yes.
Dr. Hisham?
Yes, yes.
Okay, thank you, Dr. Hisham. I really appreciate the invitation. I'd like to share my presentation now. Okay. Good evening, and thank you for attending this presentation on deep learning and AI for biomedical signal processing. The goal of this presentation actually is to introduce computer science people and other AI experts to biomedical signal processing using deep learning and AI. So they can dive into this field, and maybe we later on collaborate on some parts of this field. As we start, let me introduce you to biomedical signals, and then we will go to the deep learning, and I will give 2 examples of my research, actually, and the ongoing research on this field, which I'm doing with my master students. First of all, the signal is defined. Generally, it is any variable that carries information. So it could be mechanical, it could be voltage, it could be light, whatever the form is. And the important thing is that it carries information. Or if we want to go to the strict definition, it is a mathematical function of one or more independent variable that representing measurable quantity. This is a general for any signal, but if we talk about biomedical signal, it's the same definition, but it represents physiological quantities. So if we have a patient and we want to measure some physiological parameters like the heart activity or the blood flow or whatever we want to measure from the patient, so it can be used for the signal can be used for diagnosis or later on feedback with therapy. So if we have a patient, then we need sensors to capture the information and to translate the physical quantity or the physiological quantity into some sort of voltage or current or other form that can be processed later on. So the sensor will give us a signal that can be processed by circuit, which is usually analog circuit, which is basically electronics, amplification and basic filtering, and maybe protection circuit. So this is basically electronics, and it is a hardware. Then most of the devices use ADC converter, which is to convert the signal, the analog signal captured by the electronics into digital form. And digital form, which can be fed into a computer or a processor or any form of DSP, maybe the DSP processor or a computer or a microcontroller. So in this stage, we can do signal processing either using AI or the conventional signal processing techniques. So now we have, after the ADC, we have a signal that can be processed using computers mainly. Okay, some examples of the biomedical signals: the electrocardiogram, which represent the electrical activity of the heart, captured by a sensor. It's called the electrodes, placed into the limbs, forelimbs and chest. The data represent the heart electrical activity, and it can be used for mainly diagnosis. For example, respiration pattern. We can use sensor like piezoelectric or piezoresistive or capacitive. The data will represent the breathing pattern. We can capture also breathing rate and inspiration and expiration. Hand gesture, sensor like strain gauges or strain sensors, EMG, electrical impedance, flex sensor. It will give the hand gesture patterns. Blood pressure, for example, or arterial blood pressure, which can used by oscillometry, and arterial blood pressure, it is invasive, using a catheter, and the sensor is placed on the tip of the catheter. It represents the data that will represent the forces on the body blood vessels. One important parameter is oxygen saturation. That's the percentage of oxygenation in the blood. We use light transmitter and receiver, a device called pulse oximetry. That is usually you see in the hospital, that a device placed on the finger to capture the pulse oxygenation. The data represent the oxygen level in the blood and also the pulse propagation from the heart. For example, this is a chart of some of the signals. For example, the top panel, this is actually a real patient. Top panel represent the ECG, top and second panel represent the ECG. Then we have arterial blood pressure, pulmonary blood pressure, belt tomography. It is also represent the BPG. It is the pulse oximetry signal, and the last panel is the respiration signal. And each one of them can be processed and capture information, and can be used for diagnosis and the related site of the body. So usually we use a terminology in biomedical signal processing, which is called computer-aided diagnosis. Computer-aided diagnosis aims to detect the abnormalities in the body tissues or organs. Usually it is composed of stages. The first stage is the pre-processing of the data, reducing noise, detecting the event. It is a general pre-processing stage. Then we usually use segmentation. If you have a long chart of an ECG signal, for example, the electrical activity of the heart, so you want to segment each heartbeat and deal with each heartbeat time alone. Then we use feature extraction. Feature extraction could be time domain features or frequency domain features. And then we use the classification based on the features that we extracted. This is the general term for computer-aided diagnosis. Of course, the technique will differ. How we implement these, we'll see later on how can we implement this. But if you hear computer-aided diagnosis, it is very much like using the AI or artificial intelligence or deep learning or machine learning to implement the diagnosis procedure. And the terminology for signal processing means any type of signal manipulation. So if you amplify the signal or filter the signal, this is a type of signal processing. Mainly, we have eliminating or reducing noise, because most of the signal captured by the electronics and by the sensors mainly buried with noise. There is a lot of noise sources, such as patient movement. If you look at the patient movement, for example, it will incorporate a lot of noise. Then you have power line interference. Then you have, for example, if you are recording the heart sounds, then you have voices. If somebody talks near the patient. So eliminating and reducing noise is a big field in this area. Then we have correction of distortion. Distortion could be, for example, if you have a drift in the sensor, then this is maybe a distortion. You need to correct it. If the sensor is highly sensitive to temperature, then you have to compensate for the temperature. Then we have extraction of information embedded with the measured signal. And the last stage is event or abnormality detection. So mainly the signal processing, either one of these technique, one of these applications, let's say, in general. And now, for example, on using the signal processing techniques, for example, noise reduction. If we're gonna use noise reduction, there is a lot of literature on noise reduction. For example, using Kalman filters. Of course, this is conventional signal processing techniques. So you have adaptive filters, Kalman filter, wavelet transform, empirical mode decomposition. You can reduce noise, or some of the research on this to reduce noise in ECG or EMG signals using these techniques. For example, power line interference in medical, power line interference that's coming from the power, electromagnetic interference. This is a big noise in medical devices in general. So it can be used, for example, using Kalman filters or adaptive filters or even digital filters. The source separation, for example, source separation is also, let's say, it is a very challenging field. So if you have, for example, recording the sounds for the heart, then you will not record only the heart sounds. You will record also the lung sounds, the respiration sounds. You will record any movement in the patient chest. You will record that. You will capture that motion as a sound. If you have, for example, any voices in the room, you will capture these, and those are also noise. But Lung sound separation is an old problem. It has been for a long time, and the goal is to separate the heart sounds from the lung sounds. So you have one signal that is composed of heart sound and lung sound, and you're gonna use the maybe blind source separation to separate the heart sound and the lung sounds. Actually, this is maybe I worked on this problem maybe 15 years ago using genetic algorithm and blind source separation. So it's an old problem. Fetal, for example, another source separation, when you record the ECG from a pregnant woman, for example, you're gonna record from the abdomen. You're gonna have two ECGs, and you want to extract the fetal ECG extraction, also using blind source separation and Kalman filter or singular value decomposition. They have been used, all these techniques have been used to separate the fetal ECG. For example, event detection, if you have an ECG and you wanna detect the R wave, you can use digital filters and or windowing and or adaptive filters. For example, if you have EEG, which is the brain activity, it's a measurement of the brain activity. It's very much like the ECG, but for the brain. If you want to measure, detect the seizure detection using spectral density or wavelet transform or any form of time frequency representation, and these have been used also. These are techniques for signal processing, conventional techniques. People still working on this problem using conventional techniques. Here's an example, and I will come to this example later on. But for now, just to give the idea. But I will go deeper into this presentation using deep learning. So if we have the signal, this signal is an ECG signal. If you have an ECG signal and you want to detect the say, let me just pick the cursor. So this is the ECG signal, and if we look to the last panel, this is the respiration signal. So we have respiration signal. I'm not sure my marking is there, Dr. Hisham. My marking is there or not?
Yes.
So if you have this ECG and this is the respiration, we can, if you look to the respiration, there are some points in the respiration signal where there is no respiration. This respiration is halted. For example, this region, there is no respiration. The patient halted the respiration. So we can say that the respiration stopped at these areas. So the goal now is not, I don't have the respiration signal. I don't have this signal. Can I detect, the question is, can I detect the respiration halting or stopping the respiration from the ECG signal if I'm recording the ECG signal only? Well, this is a difficult problem. So there is a lot of literature on the relation between the QT interval, this interval, if you look here, this interval, the variability of this interval is related to the respiration. So we can detect the QT interval, and then we investigate the variability of the QT interval to find this region. Actually, this part of the research we already done, which is detecting the QT interval, and we are in the second stage to relate this is QT interval into the to diagnose the respiration, to find where is the respiration is halted or stopped. And this is very important in apnea detection. People suffering from stopping the respiration during the night, during sleep. I'll come to this to explain this more in detail, how we can detect this region using deep learning, the first part of this research. So this is an example of how we can use signal processing to detect events, for example. Okay. I'm sorry, it seems that okay, let me erase this. Now, the question is now going to deep learning. Terminology, I should say there are some terminology like AI, artificial intelligence, machine learning, and deep learning. What's the relationship between AI, machine learning, and deep learning? If we look at the artificial intelligence, it is artificial intelligence mainly is the general term. Okay, so the general term, and the basic definition of artificial intelligence, meaning human intelligence exhibited by the machine. So the machine can do tasks without mainly explicitly programming them. Okay, so this is the general term. So it can be actually it can be divided into two categories: general AI and narrow AI. General AI, that the machine can deal with a wide variety of tasks. Narrow AI is for specific tasks, or one task, or specific range of tasks. So the machine learning now, it is an artificial intelligence, but applied on a narrow AI. So you apply it for specific tasks. Deep learning is also part of the machine learning. It is some sort of machine learning, but using deep neural networks, which has usually has many hidden layers inside the architecture. So the machine learning, in machine learning, basically we need to building a model. The model will be built from data, okay, and via optimization. So we use mainly optimization to build the model, but using data. So we capture the rules, mainly the rules are captured. Okay, usual programming, when we program, for example, using C++ or Python, or without deep learning, we put the rules. Now the rules will be captured. Okay. In general, machine learning steps are can be stated, but this is again, this is in general. So the first step, let's say, it is a problem definition. You have what you want to model. For example, our example before, I want to model the Q interval estimation, or I want to predict the blood flow, or I want to predict the or classify the arrhythmias in heart. Okay, so this is the basic problem definition. Then we have the data curation. We need the data in the medical field. This is I have to pause here for people they are not in medical engineering. Data is very important in the medical field. There is a way. First of all, you have data banks, databases available on the internet for most of the signals. You can download, you can use it, you can try your implementation on them. But if you want to collect yourself data, there is an IRB, which is Institution Review Board agree on the data collection. So you have to obtain IRB before data collection. Okay. The other thing, if you want to work on this, the labeling is very important. Labeling the data is very important. Also, diversity is very important. I will talk about diversity when I give the example later on. So the diversity is very important in medical field, diversity of the data. Then the next stage is architecture design. So what type of neural network, for example, you're going to use, loss function selection, loss function selection, so you can determine which model is good. Then the optimization method. So so these are the stages for the general machine learning. So we have optimization. We have optimization technique. This optimization technique will tweak the architecture parameters. Okay, the architecture parameters. For example, if you take a conventional network, you're gonna use the weights. You cannot change the weights. These are the parameters for the neural net. The weights and the bias. So you use optimization to tweak the architecture parameters to minimize the loss function averaged over the data. So this is simply the machine learning. So you use optimization to tweak the architecture parameters, the model parameters, to minimize the loss function average over your data. Okay. So try to remember this optimization to tweak the parameters to minimize the loss function or average over all your data. So if we have training data, then if the data is labeled, your data is labeled, you have marking for the ground truth. You have your ground truth. Okay. If you have it, you can use, for example, supervised learning, or if you would like to use also unsupervised learning. So you have the machine learning. It could be either supervised or non-supervised or semi-supervised, and each one of them has its for example, clustering, or you use, for example, k-means clustering, or embedding, or use generative models, or use support vector machine for classification, decision tree, or regression. Okay, so you have either you could be using supervised or unsupervised or semi-supervised, as shown in the figure. Now let's say let us look at the example using conventional machine learning and deep learning. So if we have a supervised learning and our architecture is conventional machine learning, you can use, for example, support vector machine or random forest. Okay, deep learning, you could use convolutional network or RNN, LSTM, or GRU. And these can be used, for example, for ECG, EEG, EMG classification, seizure detection, BBG classification, gesture recognition, supervised learning. If you look at unsupervised learning, you could use also conventional, you could use k-mean clustering or BCA. Deep learning, you could use autoencoder. unit, for example, unit also 2D or multi-channel unit for cluster patient by arrhythmias, for example, dimensionality reduction, heart-lung sound separation. Okay, and these have been used for in the last maybe 4 years. There are some publications on these examples. These examples actually publications. So processing example, the main example. Let's see one of the examples. This is example one. I will go now in deeper on this. Mainly the problem in definition. Let's look at the problem. So the problem is to recover heart sounds captured from electronic stethoscope in a clinical environment. Okay, so what I'm doing, measuring the heart sounds from the patient chest. Clinical environment means that we are recording in the hospital, not in controlled environment. Yeah, I mean, not in the lab or in a silent place. It is a clinical environment. So we are recording at the hospital. You cannot control the noise sources here. Okay, so this is very important. So when you do research, people, especially in medical, people are interested in doing the measurement in the clinical environment. It's not controlled environment. Okay, so we want to recover heart sounds to in order to use it for diagnosis. So in this problem, our goal is to recover two goals. We have recover heart sound, including any murmurs that indicate pathological condition. So if the sound, there's murmurs in the sounds or changes in the sounds or any abnormalities in the sound that indicate pathological condition, we need to recover that. We don't want this to be considered as noise and removed. We also want to reduce respiration sound, electronic noise, human voices, movement noise, and these are you're gonna see them captured. If you are doing a clinical environment, you will see these noises. The electronic noise is coming from the electronic stethoscope, from the thermal noise, could be thermal noise or flicker noise that's coming from the electronics in the stethoscope. So this is our problem, and the question is how we can recover the heart sounds. Okay, there are many techniques and unconventional signal processing, mainly in the area of blind source separation. They manage to recover heart sounds, okay, or separate heart from lungs. This is an example of the recorded signal or captured signal. Each pulses here is a heart sound, is a beat, represent one beat. Okay, if you look at that, between the beats there is noise between the beats, but you cannot say that I have, for example, respiration. I'm not seeing any respiration noise in this figure. This is the spectrum. The second panel is spectrum of the wave of the waveform. Another example, which is it's not clear like this one. This is one you can say each beat, you can determine each beat where is it, but here it is somehow difficult. This is a sound, a heart sound with pathological condition. But if you look at the time, let's say at 0.5 second, there's a lot of noise here. If you look at the time between, for example, 2.5 to 3 seconds, there is a lot of noise somewhere here. So can I capture this while keeping the information, keeping the pathological sounds there? This is the main question. Okay. So the main idea, what we did actually in this research is we managed to recover the sound. But my question to you, I wanna just see if you follow me or not. If you have this signal, how can I differentiate between the hard sounds and any other noise? I mean, how can I say this part is hard sound or the other is not, is noise? How can I differentiate? Is there a way to visually, I mean visually, or by signal processing, or by not a deep learning, I mean just by looking at the signal, can you say this part is noise and this part is not? Based on what? Anybody can answer this question?
Maybe a predefined range of frequencies for a specific signal.
No, I visually. I want to do it visually. You don't have any tools. You don't have signal processing tools. You don't have, for example, just visually.
If I see maybe that there's like a bunch of data at the same time, like
Bunch of
maybe
what?
maybe at the start we can see like there's a lot of noise. There's like a high peaks, very high frequency. So that gives me that there's noise.
Okay. Anybody? Okay. Anybody? Okay.
Knowing, like,
The-
simply knowing what is the true, like, the non-pathological, or like the
Yeah. How can you
optimal one.
detail? You don't know the truth.
Hmm.
But visually, how can you say this is most likely to be hard sound, or this part most likely to be noise?
Like maybe clinical knowledge, we have like the S1 sounds, S2 sounds, and in between it has to be noise. Like,
Yes. Yeah. But okay, if you look in your mind, okay, and look at the repeated patterns, most likely the repeated patterns will be hard sound or noise.
hard sound, it's like deterministic pattern, somewhat deterministic. So
Somehow, it's not deterministic. It is not. It is a random signal, but the repeated pattern, right? The noise. If you look at the first part before 0.5 second, for example, this is not repeated, right? While the two peaks at, for example, 1 and 0.5, this is somehow repeating. So in your brain, you can filter repeated patterns, right? And the repeated pattern most likely hard sounds, okay? Because it will repeat itself each heartbeat, right? So what we did was we consider this, okay? We consider the repeated pattern. So we use a time frequency representation as some sort of presentation. If you go to time frequency representation, there is Weber transform, there is Fourier transform, right? We use a transform called modified cosine transform. Modified cosine transform can give us better frequency resolution, and it can remove the blocks effect. The edges between the blocks effect will be minimized. So if you have, for example, this top panel is a sound, hard sound, then the first image, say which is the second panel, is the modified cosine transform. Now if we apply this repeated pattern and find the repeated spectrum, okay, so we end up with the third panel. If you look to the third panel, it's very smooth. So you are removing unrepeated pattern from the spectrum, and you end up with only the repeated spectrum, right? Okay, so this is the basic idea, the basic, let's say, input for our deep learning or machine learning system. We could use inversion of this and use traditional signal processing techniques to inverse this and end up with the repeated spectrum, but you end up with maybe you will lose some of the information regarding the pathological condition. So if we have this, we could use deep learning, or we use deep learning to recover the heart sound. So if we have the heart sound and we have the mix, so this is during the training, for example, this is the architecture during the training. So we have the heart sounds and the mixed sounds, and then we feed the heart sound and obtain the modified cosine transform, and the mix is fed into our neural network. The neural network is or the deep learning, say, network use two criteria for modification, or two stages of modification, or criteria for optimization. The first is using the cosine transform domain, and the other using the time domain, which is we inverse the signal after masking, and then we also obtain the criterion to for optimization. So we have two criteria for optimization. One is coming from the cosine domain, cosine transform domain, and the other one from the time domain. Okay, so if we have, for example, this is the D, this is the network structure. So we have the mixed sound, then we partition the signal, do modified cosine transform, obtain the beat MCT, which is the repeated pattern, do some normalization and conversion to dB, then feed it into bidirectional LSTM, 2 stages, and you will end up with the recovered or the masked MCT. Okay, and then you do inverse MCT to obtain the time domain signal. This is one example of the results. For example, this is one signal. If you look at this, we have the top panel is the mixed sound. Okay, second panel is the true heart sound, and this is the recovered. The third panel is the recovered sound, and the last two panel is the noise. If you look at the noise, we actually remove the noise, so the signal is almost very clean. So the area around 1 second, it has noise. Okay, so this is one example. This is another example with respiration artifacts. So the dense areas, the 3 dense areas, these are respiration. So we can we remove the respiration and capture the heart sound? If you look, the second panel is the heart sounds. Very much we removed the respiration, and the last panel is the the recovered lung sounds or the respiration sounds. So it did very good job in recovering the two. This is the source separation. So we have one signal, and we separated this signal into two components: the heart sounds and the lung sounds. Okay, the issue here in this, for example, in this problem, regarding the diversity of the data. So if you just work on one database or use one database, you cannot use that for a clinical use, because one database it's not diverse. Even if you create many datas, many voices, many sounds, but still you are doing most likely you will capture the behavior of your system for capturing the sounds. So in this research we used we collected data already. We collected data and then we use also data from internet, many data from internet. We use different noise, and the testing we did testing on in a totally different databases. So it's not seen by training. Okay, so what you're seeing here is not seen by training. So the result, we convinced it can be used for a clinical environment. So this is what I meant by when you use clinical environment. In a clinical environment, use diverse data from different measurement system, from different measuring people. You know, reproducibility and repeatability should be considered for this. Okay. The second example, which I already mentioned at the start of the presentation. So if you have one heartbeat, this is one heartbeat, and the heartbeat, this is the electrical activity of the heart. It's called ECG signal. So if you have this waveform, and it is characterized by different waveform like P, Q, R, S, T. And our goal is to determine the QT interval. Okay, the QT interval. So this is the Q interval. It is being used for diagnosis and other for example, if there is elevation or prolongation, it indicates some pathological conditions. But what we are interested in is to relate the QT interval to the respiration. So we can use this variability, the Q interval variability, to infer some information about the respiration, and to use it for people with respiration problem, or halting, or stopping respiration, or apnea. Or so this is the problem. How can I find the QT interval? Okay, this is for example textbook ECG, but when you look at the patients, the waveform could differ. Okay, so what we did is so we have one heartbeat, we extract one heartbeat. So the processing is not done on the, usually you record, for example, 5 minutes of data or 10 minutes of data, but we extract each heartbeat, feed it into LSTM network, 2 stages, to predict the waveform. So we feed the one heartbeat, and we predict the QT interval, the waveform, not the interval. We predict the waveform. So here we have the predicted waveform, and then we use another network to estimate, or deep learning, also LSTM, to estimate the QT interval. So we have two networks, or 2 deep learning systems. One to predict the waveform, and the other one is to estimate. Okay, the question is, why don't you use one and use it to estimate directly? You give the beat, and then you estimate the QT interval. The question is, it's not like easy. It's not easy like that. Sometimes we have a QT interval that is difficult as a waveform. It's not always the same shape, always the same timing. So prediction is better. So you eliminate the changes in the beat itself. Okay. Here's what we have. If you have an input ECG, for example, this is the input beat, and this is the predicted waveform. So we predict the waveform. Okay. And the green is the start and end marking. Okay, so there's 3 different waveforms, so or 3 different beats. So this is the predicted waveform. Okay, then we use it to estimate the QT interval. Also, here we have example after we estimated the QT interval. This is not predicted, this is a waveform. So these are 4 ECG signals, 4 ECG different ECG signals, and it can be seen did very well in predicting the or estimating the time interval. Of course, we evaluated the system using planned plots, and we compare it to the other methods. And I'm just showing the basic results to give you an idea on the medical signal processing. Okay, then the next stage which we are doing is to take the variability, which is we are working on right now. This is already published, but the next stage is to relate this to the respiration. So my goal is to detect apnea cases or respiration pathology and or pathological condition related to respiration using the QT interval. Once I have, so I record only the ECG and obtain information from the ECG for respiration. The ongoing research, actually, I'm not sure one of my students is here. We are working on another topic, which is called physically informed deep learning or physically informed neural networks. And this is very interesting. And this is, I think Osama is here. His topic is in this area, and physically informed. Basically, you have a differential equation that represents the some variable in the body, for example, blood flow or blood pressure, or it is governed by a differential equation. So you build a model, but you feed the equation, the governing equation, into you incorporate the physical, the differential equation into the deep learnings. Either you optimize the loss function using that, or in any of the stages of the deep learning. This is also an ongoing project with Osama. Hopefully we get results soon. I'm open for any questions, and this is my email. If you would like, if you need further information on the maybe on the talk or the research presented, or you want to collaborate, or you have any question on this regard. All this, of course, this is all implemented in Python, mainly PyTorch. So if you have questions, feel free to ask.
I have a question, or if you someone
شايف جهاد بده يسأل.
you can ask.
Yes, go ahead.
بس كنت بسأل إنه ايش هي الايفالويشن متريكس، يعني المعتادله to compare التراديشنال ممكن نحكي decomposition denoising methods عن الديب learning methods بشكل عام. يعني هل هي مثلا simply deviation, square deviation او شيء زي هيك، ولا في اشياء ثانيه مخصصه؟
denoising
بشكل عام يعني to evaluate الايفالويشن متريكس المستخدمه اذا بدنا نقارن مثلا.
You could use there are a lot of metrics. You could use, for example, signal to noise ratio. if you have a signal to noise ratio. Okay. Actually, it depends on the waveform. If you talk about sound, there are a whole bunch of metrics that been used in literature. But if you talk in general, for example, ECG or fetal ECG with the mother ECG, for example, you could use, for example, mean squared error. Okay, but
Okay.
for sound there is maybe 4 or 5 parameters. I cannot remember now, but it's being used for it is related to the signal to noise ratio.
Okay, thank you.
دكتور بهاء تفضل.
السلام عليكم، الله يعطيكم العافية جميعا. يعطيك العافية يا دكتور عوض. يعني مبدع كالعادة ورائع، الله يجزيك الخير وبارك الله فيك. دكتورنا أنا عندي استفسار بخصوص الميديكال hypothesis behind relation بين ال QT period and halting of the breath in general. كيف يعني على أي أساس بنيتوا الهايبوثيسيس تبعتكم؟ يعني إيش الأساس البيولوجي لإلها من فضلك؟
It is not. هو it is being there, دكتور بهاء. There is maybe 4 or 5 papers investigate the relationship between QT interval and the respiration. Okay, there is a relation, but it's not the direct. Our investigation, it's not a direct. So the QT interval is very sensitive to other parameters. Okay, one of them is this is the difficulty in the problem. Okay, one of them is the respiration, but it's not our hypothesis. It is being there.
Oh, I see. يعني is it مثلا is it instantaneous relationship
It is mainly دكتور it is mainly modulated by the respiration.
Okay, بارك الله فيك. Thank you.
دكتورة يسرا.
Thanks, Dr. Awad. يعني it's been a long time since the last lecture that I attend for you. It's very interesting. Dr. Awad, أنا صراحة I got confused when I heard about heart sounds and ECG. Like I usually work on ECG, an ECG signal, but I mean I don't deal with heart sounds. Do we use the same electrodes or leads to measure the heart sounds, similarly to what we do for ECG signal?
Okay, it's not been a long time, Dr. Isra. I'm not that old, huh?
No. 2010.
Yeah. The ECG is different than the heart sound. The heart sound is captured by stethoscope, mainly microphone. You capture sound, but the ECG you captured electrical activity of the heart. So this is a different techniques. Okay,
So
but mainly
no
if you want to measure the heart sounds, you know the stethoscope, the normal stethoscope that the medical doctor use to hear the sounds. We have also electronic stethoscope that you can use it to get analog signal, and then you feed it into the computer. You do data acquisition.
What type of leads that are used for this, for the heart sound measurement?
It is electronic stethoscope. It's a microphone.
Okay, it's just like a microphone. So it's not related to the ECG leads that we usually...
No. The ECG, you record the electrical activity. You use electrodes, and this is different power.
Okay, thank you.
You're welcome.
أسامة.
Did you mean me?
أسامة لسه.
Okay, so I wanted to ask about the LSTM models that you used, because each one had a different resolution going in. It was 3-dimensional, and you used 5, 2 at the start and 3 at the end. So how do you decide how many LSTM models do you use and the resolution that you use?
Oh, this is the architecture I said before, to determine the architecture for the program, and this is mainly the LSTM is known for the memory, long-term memory. So you can, it's very much like you, it will remember the past inputs. Okay, but the actual architecture, it's we've tried many architecture, many layers to, or bidirectional to get the optimal one. It's not a straightforward. It's not a magic. So you plug in and you end up with. We have tried many configurations, many architectures to obtain the best one.
Okay, another question is following that, since after STM we got as transformers, right? And they use them in the general purpose language models. Can we use transformers to kind of push that prediction further, make it better instead of LSTM, or am I wrong?
Yeah, you could use.
Okay. I
Well,
see.
you will see that on your master works.
Okay.
We'll try different architectures, different. Yeah.
Okay. Thank you.
في سارة حامد.
السلام عليكم، يعطيك العافية دكتور. سؤالي عن أول بروبلم when you separated اللي هي الهارت signal عن اللنج signal. From what I understand, the basic idea is that the heartbeats are repetitive. They have a repetitive pattern. But isn't also the breathing or the respiratory signal also have a repetitive pattern?
Yes. Yeah, that's actually a very good question. This is yes, respiration is also repetitive. But if you when you do segmentation, because we are not dealing with the whole record of the data, we segment the data, so the data is segmented before the feeding into the system, right? Okay, so if you segment the signal, so you in your segment you have 2 or 3 breathing pattern, then you capture the breathing pattern. You will not do anything. So the respiration is usually slower than the heartbeat, right? So if you can capture, you can make your segmentation such that it only captures the, let's say, 4 or 3 cycles of heartbeat and probably 1 respiration cycle. So it's not repetitive in this sense.
Okay,
You
I
got it?
Thank you. Yes, thank you.
في أسئلة أخرى ضل بابا جهاد.
نعم، يعطيك العافية دكتور. بس بدي أتأكد أنا من شغلة كانت في ستيب مسمى partitioning قبل ال STM. هاي البارتيشنينج هي بس إنه تايم دومين، يعني زي regular interval، ولا بتكون برضه frequency related، يعني decomposition أو شو؟
No, time domain. All partitioning is time domain.
أوكي شكرا.
I didn't describe the architecture. My plan is just to introduce the general idea. But these are the two research I published last year. So in details, I mean. So
في أسئلة أخرى.
okay, feel free to email me if you have any question, or if you need more details, I can answer more details, or if you have any idea or you want to collaborate on this topic, or whatever you need, I'm available at this email.
Yes, I think the lecture has opened a lot of questions that maybe could be answered by looking at your relevant papers or by direct communication with Professor Awad. I would like to conclude this evening with thanking Professor Awad for his time and his dedication for this lecture. I think we confirm we all had a very nice evening by getting a lot of new information regarding the use of deep learning in biomedical signal processing. Thanks a lot, Dr. Awad, and thanks for all attendees. And I hope we can meet later in the coming sessions.
Thank you.
يعطيكم العافية جميعا. شكرا.
Thank you very much.